We've spent some time the last couple of days talking about energy, kinetic energy, potential energy, energy of motion, stored energy. And we talked a little bit about the change in energy. Today we want to talk more about the change in energy. That's what we define work as. Work is the change in energy that's experienced by an object, the gain in energy or the loss of energy that's experienced by an object as something is done to it. If I'm at the bottom of the hill and I walk up the hill and I have zero potential energy at the bottom of the hill and I have 5,000 joules of potential energy at the top of the hill, then my change in energy is 5,000 joules. The work done by me as I climb up the hill is 5,000 joules. If I go down that hill, the work done is negative 5,000 joules because I would have lost 5,000 joules of potential energy. The work is the change in energy experienced by the object. And it depends upon two things. In order to change the energy of an object, we need to do two things. Number one, Jacob's desk right now is not moving. Jacob's desk has 0 joules of energy right now. What do I got to do to give Jacob's desk energy? What do I have to do to his desk to change the energy of his desk? I got to apply a force. I got to push it. Okay, when I push it, it starts moving. It gains energy. I have to apply a force. But force isn't enough. Yeah, I can apply a force on his desk. Look, I'm applying a force right now on his desk. What's happening to it? Am I changing its energy? No. Not only do I need a force, but I need, what's the difference between this and this? Force and movement. I need a displacement. Okay, you can apply a force all you want. If the object doesn't move, its energy isn't changing. But if you apply a force and there's movement, then you're gaining energy. So we need a force and we need a displacement. Now, seems simple, right? But it's not quite as simple as that. Okay? Right now, Jacob's desk is at rest. But let's pretend that it was on ice, and it was moving because maybe somebody else pushed it. Maybe Christine pushed it, and it was just still moving because it was on ice. Right? That's displacement. Let's say that I push downward on Jacob's desk. I don't do anything to its motion. It's moving horizontally because Christine had pushed it a while ago, and it's still moving because it's on ice. I'm pushing it downward. There's a force, there's a displacement, but I'm still not doing any work on his desk because I'm not changing the energy of his desk, right? If it's moving horizontally and I push it downward and it keeps moving horizontally, I'm not changing the energy of his desk. So not only do we have to apply a force and have movement, a force and displacement, but the force and displacement have to be parallel to each other. So in other words, if the movement is to the right, if I want to do work on this desk, then I have to push it to the right or to the left in the same direction or the opposite direction. In other words, I have to push it parallel to the direction of motion. Otherwise, the motion that it experiences is completely independent of the force. You sit in your car goes horizontally to the north on the highway. You apply a force of gravity on the car because you have mass. You're not doing any work on the car because the force is down and the motion is horizontal to the north. You're not contributing to the motion of the car. You're not increasing or decreasing the energy of the car. But if you stand behind the car as it's starting to move and you push it and it moves faster as a result of that, then you're doing work on the car because you're applying a force, there's displacement, and the force and displacement are parallel to each other. Now, if they're perpendicular, there's just no relationship. But if we pull on Jacob's desk like we pull on a wagon, then part of the force that I'm applying, look, I'm pulling at an angle of 30 degrees right now. Part of the force that I'm applying is parallel to the motion of Jacob's desk. Part of it is not. So what do we got to do? Well, if it's completely parallel, perfect. It's force and it's displacement, we got it. If it's perpendicular, well, perfect, because there's no work done. Because I'm pushing perpendicular to the direction of motion. But if I'm pulling at an angle of 30 degrees, 40 degrees, 50 degrees, whatever, then part of the force that I'm applying is changing the energy of the object. So what we got to do in that case, if they're perpendicular, zero work. If they're parallel, then we're in good shape here. We just need a simple equation. And if they're not perpendicular or parallel, then we need to take a component of the force that is parallel to the displacement. In other words, I'm pulling it this way like the wagon. I need to find the x component of my force because that's the component that is changing the energy of the wagon. Not the y component, just the x. Now, let's try to establish an equation for work here. The work, the change in energy. Whoops, that's not W. That's I don't know what that was. Let's say W is equal to, well, we defined it as change in energy. So let's say W, first of all, was equal to delta E. But let's also say W is equal to, well, if it's dependent upon force and displacement, the equation will be force times displacement. But it's only that equation. That equation is only valid if the force and displacement are parallel to each other. If they're not parallel to each other, we need to find a component that is parallel. If here's my force, and my displacement is this way, and this is, let's say, 30 degrees, if I want to find the x component of my force, the x component of my force that's parallel to the displacement, I'm going to use a trig function, right? Which trig function would I use to find x here? Cos. Yeah, so it would be cosine 30 degrees is equal to x over the hypotenuse. Because it's always the same in these questions, what I'm going to do is actually just tack on the cos theta on the end of this equation. So that cos theta will get for us the x component of the force when the force and displacement are parallel. Everybody take out your calculators right now. I want you to try something. So Jacob's desk is moving horizontally because Christine pushed it a few minutes ago and it's sliding on ice and it's moving horizontally. And I pushed downward on his desk. The angle that I'm pushing downward relative to the way that's moving is 90 degrees, right? How much work do you think we're going to do on that desk? Zero. Try going cosine 90 on your calculators right now. What do you get? Zero. So F, whatever the force that I applied was, times the displacement of the desk times 0 is 0. In other words, I didn't do any work on the desk, right? Okay, so let's say Jacob's desk is moving horizontally because I'm moving it horizontally, right? It's moving to the right because I'm pushing it to the right. What's the angle there between the way that I'm pushing it and the way that it's moving? I push it to the right, it moves to the right, the angle is 0. Hit cos 0 on your calculator. What do you get? 1. So if I move it in the same direction as I push it, the equation is F times D times 1. In other words, the equation just becomes F times D. Does that make sense? So F is going to stand for the force. D is going to stand for the displacement. Normally, you want those to be parallel to each other, but if they're not parallel to each other, you just got to tack on the theta there and get the component that is parallel. So theta stands for the angle between the force and displacement. It's not just any angle. It's the angle between the force and the displacement. So for instance, if here's a box, I pull it this way and it moves this way, the angle is 0. I pull it this way at 30 degrees and it moves this way, the angle is 30 degrees. What about this one? The angle of the hill is 30 degrees, and I pull it this way up the hill. It moves up the hill. What's theta in this case? Oh, See if you can get this one. 0, good. Despite the fact that I'm pulling it up the hill, it doesn't matter, right? Because I'm pulling it up the hill and it's moving up the hill. It's parallel. So in that case, we don't want to just take a random angle just because we have a theta at 30 degrees right here. We don't want to just randomly say, whatever I have is what I sub in there. We've got to think about it. The angle in this case is 0 degrees because it's moving parallel to the direction that I'm pulling it. So here's the rule of thumb. If you have an angle between the way that you pull it and the way that it moves, FD cos theta. If you pull it in the same direction it moves, you can just drop the cos theta because cosine 0 is equal to 1, and the equation just becomes F times D. Okay, but only if the force is parallel to the direction of motion of the object. Okay, we got a couple examples here. The first one is from your textbook. The second one is my own example. First one says, figure 6.8 shows a force of 150 newtons acting while an object moves 25 meters at 25 degrees while the force acts. What's the work done by this force? We know that work is equal to delta E. Is that going to help me in this case? No. We also know that work is equal to F times D times, do we need the cos theta here? Yeah, because there's an angle between the way that I push it and the way that it moves. Let's sub in our numbers here. I got 150 newtons times the displacement of 25 meters times cosine 25.0 degrees. Let's see what we get. Uh, 3398. We're going to say 3.40 times 10 to the 3. And what would the units for work be? Joules. Because it's energy, right? It's change in energy. And it's going to be a scalar as well, just because energy is a scalar. I'd like you to take a look at page 294 right now. I'm going to ask you to do the first 3 questions right now, the first 3 questions on page 294, please. All right, let's have a quick peek at question number 3 here. It says a force of 640 newtons does 12,500 joules of work over a displacement of 24 meters. What's the angle between the force and displacement? So clearly, if they're asking me for the angle, the force and the displacement are not parallel. So what we effectively have to do is find the parallel component of the force and the displacement. And to do that, we're going to use the equation W is equal to F times D times cosine theta. Remember, we can drop the cos theta. We can drop the cos theta if there is no angle between the way that it moves and the way that it's pushed. There is here, and we've got to find that value. What I want to do here is rearrange this to solve for theta, which is a bit tricky. So let's start off by just rearranging this to solve for cos theta. Cos theta would be W over F times D. Right, take the F times D over by dividing, we end up with W over F times D. That's cos theta. Now we want to solve for theta, we're going to take the inverse cos of all that. So the second function cos of W over F times D. Some of you may wish to calculate that number first and then say, let's take the inverse cosine of it. Some of you may just like to do it like this, doesn't really matter. Bottom line is it's the inverse cos of W, which is 12,500. F is 640 newtons, and displacement is 24.0 meters. So let's get that number inside the brackets first. Let's say 12,500, divide it by, and then use some brackets on the bottom. 640 times 24 gives me a value of 0.813. Let's take the inverse cos of that, and we end up with 35.5 degrees. Does that seem reasonable? Yeah, I think so. How many people got 35.5 degrees there? Okay, good. Okay, so if the angle is 0, if it's moving parallel to the way it's pushed, just drop the cos theta. If it's not 0, if there is an angle, and clearly there is in this question, as is in question number 1 and 2 as well, then make sure that you include that angle, okay, even if you're trying to find that angle. All right, let's take a look at one more work example here. It says a 20 kilogram object gains 300 joules of kinetic energy as it's pushed a distance of 100 meters. Calculate the force used to push the object. We're going to assume that the force is parallel to the direction of motion. Should have said that in the question, but we're going to definitely assume that. So that means that we don't have to worry about a theta in this question. There is a theta, but it's 0 degrees, and cosine 0 is 1, so the equation becomes F times D. But how am I going to deal with this, right? I want to find the force used to push the object, and I've got the displacement. Probably going to be a work problem, W is equal to F times D, but I don't know what work is. Any ideas? Do I know what work is? Yeah? Yeah, work is the change in energy. And it's also equal to the force times the displacement. Force times displacement times cosine theta, but theta is 0 here, so it just becomes F times D. We know delta E. It's 300 joules. And we're looking for the force, and the displacement is 100 meters. So we're going to simply say F is equal to 300 divided by 100, and F is equal to 3.00 newtons. So the key there is recognizing that, as Blake did, the work is the change in energy. So even if it doesn't use the word work, sometimes you have the value of the work, even when it doesn't say that. One more question. It's kind of similar to the last one, but a little bit harder. It says, 1,200 kilogram car accelerates from rest at 90 kilometers per hour over a distance of 200 meters. What's the work required to do this? What's the net force required to do this? Firstly, we've got to recognize that we've got to convert that to meters per second. We're going to say VI. Let's write down some givens on this one. VI is 0 meters per second. VF is 90 times 1,000 divided by 3,600, or 25 meters per second. My mass is 1,200 kilograms. My displacement is 200 meters. Displacement is in the same direction as the force, we'll assume. We want to find the work, and we want to find the force. Once we get the work, the force is easy. It becomes just like the last question, but trick is the work here. How do you find work without force? Well, the work, in addition to being equal to F times D, is also equal to delta E. We don't know what delta E is, though. Oh, but wait. It's final minus initial energy. And the final energy is kinetic energy, and the initial energy is 0. So if you want to find the work here, let's just get the final kinetic energy, because that's the change in energy, right? 1/2 of 1,200 times 25 squared. Gives me a value of 375,000, which we're going to round to 2 digits here. 3.8 times 10 to the 5 joules. Well, then once we have that, though, once we have that, it's easy. W is equal to F times D. We have the work. We have the change in energy. So we'll just say the work, or the change in energy, whatever you want to call it, divided by the displacement. $1,875, or 1.9 times 10 to the 3.